Hi students, welcome to today's lecture on artificial neural networks. In our earlier sessions, we have discussed about multi-layer feed-forward neural networks and the training algorithms used in that multi-layer feed-forward neural networks, that is backpropagation algorithm. Today, we will start Unit 5, which covers another special type of neural network, that is radial basis function neural network. And we'll see what are the training algorithms used for RBF neural networks and what are the special activation functions used with RBF neural networks in this unit. So before we actually begin that, what is a radial basis function neural network? First, we need to understand few basic things with respect to that radial basis function neural network. In this class, we will focus on the fundamentals required to understand and design that radial basis function neural networks. So our today's topic and focus is pattern separability and interpolation, two fundamental topics which are essential for understanding how radial basis function neural networks can be designed. So let us start with our syllabus by viewing the syllabus of this unit 5. The topic is radial basis function neural networks. That is our topic in unit 5. And we have these are the subtopics we have in this unit 5. The first topic is pattern separability, which discusses about how the input patterns can be separated, what are the possible ways of separating the input patterns. Also, we'll go through a covers theorem, which is useful in understanding the separability of patterns. And then we'll focus on interpolation problem. We'll discuss about what is an interpolation problem and how it can be solved using the special activation functions. We'll see this as our second topic. And then a little theory about what is regularization in neural networks. Okay. Once we understand what is regularization and how it helps the neural networks to converge quickly, then we will see how this regularization concept is useful in designing the RBF neural networks. So we'll discuss about regularization and RBF neural networks together. And then once the introduction to RBF neural networks is completed, we'll start designing the RBF neural networks, and also we'll practice how RBF networks can be trained using the training algorithms. We'll practice some problems also, example problems of design of RBF neural networks. And finally, we will discuss about the approximation properties of RBF neural networks to close this unit 5. So these are the topics we are going to cover in this unit 5. Let us start with our first topic, pattern separability. The pattern separability, as the name itself indicates, that there will be a set of input patterns, and we are going to look at it whether the input space is separable or not, and how many types of separations we can perform in this. So that is the topic we are going to discuss now. Okay, so let us start it. When a radial basis function neural network is used to solve a complex pattern classification problem, then the problem will be solved by transforming the corresponding input space into a high dimensional space using some nonlinear functions. Okay. So the basic point we need to understand here is, if the problem under consideration is a complex problem and the space input space is low dimensional, then it is not possible to design any neural network for the corresponding input space. Therefore, what we will do is, the low dimensional input space need to be converted into high dimensional input space such that the high dimensional input space is linearly separable. Okay. So generally we follow this particular transformation whenever we try to design a neural network for a complex pattern classification problem. Okay. So this is actually proved by the Covers theorem. So you need to understand what is a Covers theorem and what is its statement. Let us see the statement of Covers theorem. It states that a complex pattern classification problem cast in a high dimensional space non-linearly is more likely to be linearly separable than in a low dimensional space. So the point is very clear here. If the input space is a low dimensional space, then it is difficult for us to design a neural network. Whereas if the input space, if it can be mapped into a high dimensional space, then we can easily design. So it is more likely to be linearly separable. Therefore, we can easily design any kind of neural network that we want. Okay, because starting with the perceptron neural network, uh, continuing with the multi-layer feed-forward neural networks and RBF neural networks, all these are suitable for designing linear separable input patterns very easily. But in case of linearly not separable patterns, it is a bit difficult to design the neural networks. Therefore, it is always more likely to design a neural network for a complex pattern classification problem if the input space is a high dimensional space. Okay, so that is what Covers theorem is stating. To understand this, let us consider some technical definition about this. Consider a family of surfaces, each of which divide the input space into two regions. That means we are dealing with a binary classification problem. Okay, so we are dealing with, because the input space can be divided into two regions, means we are dealing with a binary classification problem. Okay. Now, let this X denote a set of input patterns. There are n input patterns assumed like that, X1, X2, so on, Xn. So these are the input patterns that we want to classify, and I assume that each of these input patterns can be assigned to one of the two classes, X plus or X minus. So two types of classifications are there. So it is also called as binary partitioning or binary classification problem. So this is called as, remember this name, the technically this problem is called as dichotomy. Dichotomy or binary partition or binary classification. Okay. So what we have here, we have n input patterns labeled as x1, x2, so on, xn, and each of these input patterns can be classified into either x plus or x minus. That means x1 may be belongs to this x plus class or may belongs to x minus class. Similarly, x2 may belongs to x plus class or x minus class, and so on. So if you consider any input pattern, it falls into one of these two categories, either x plus or x minus. Okay, so what is the name given for this kind of scenario? It is called as dichotomy. If the input patterns falls into exactly two classifications, then we call it as a dichotomy or binary partition. Okay, now, so for each input pattern x belongs to x, we can define a vector made up of a set of real valued functions as phi of x is equals to phi1 of x, comma, phi2 of x, comma, so on, phi n of x, all to the power t. That is this is actually to define your new values into a column vector. Okay, so what we are doing here is we are defining a function, a nonlinear function that converts your input space of x1, x2, so on, xn into a high dimensional space. Okay, so we are using this function for that purpose. So we'll understand. Suppose that the pattern X is a vector in a M0 dimensional space. Please see that carefully. If the input space is M0 dimensional space, then the vector phi of X maps the input space from M0 dimension to M1 dimension, which is definitely going to be higher than M0. What we are doing is from a low dimensional space, that is from M0 dimension, which is low dimensional, we are converting the input space into a high dimensional space, that is M1, okay, with high dimension, with the help of the vector that we defined here, that is phi of x is equal to phi1 of x, phi2 of x, and so on, phi n of x. So for each input value, you can use a separate function, nonlinear function, to map it into a high dimensional space. Right? Okay, so once we define that function, now the dichotomy x plus comma x minus of x is said to be phi separable. Based on how many functions you define, we say that it is phi separable if there exists an m1 dimensional vector w such that it satisfies these two formulas, these two inequalities. So what are the inequalities that should be satisfied here? It should satisfy w power t, the transpose of weight vector, into phi of x, that the calculations, the high dimensional input space is greater than 0. Okay, so if it satisfies this inequality, then we can say that x belongs to the class x plus category. Okay. Similarly, if w power t into phi of x is less than 0, then it belongs to x minus class. Okay, so we are defining how we are going to classify the input patterns based on the new linear function, a nonlinear function we define, and a weight vector selected. Okay, so how this nonlinear inequality groups the input patterns into dichotomies? It is by using the inequality w power t into phi of x greater than 0 means that the input pattern x belongs to this class x plus. If w power t into phi of x is less than 0, then x belongs to x minus class. Okay, so these two are inequalities. But whenever we say w power t into phi of x is equals to 0, then it defines the corresponding hyperplane, uh, usually going to be a straight line that separates the patterns into two distinct uh, classes. That means on one side of that hyperplane, we will have all the input patterns that belongs to x plus, and on the other side of hyperplane, we will have the input patterns that belongs to x minus. So it clearly divides the input patterns into two classes, x plus and x minus. Okay, so this line w power t into phi of x is equals to 0 line becomes a straight line that linearly separates the input patterns into two classes. Okay, so that is the separating surface. We can say like this: x defining w power t into phi of x is equals to 0 will become the separating surface of the input space. The original input space can be now linearly separable. Okay, so this is what the covers theorem says, and we have seen some technical terminology also to understand that covers theorem. Now let us focus on a simple example to understand how the input patterns which are in low dimensional space can be mapped to a high dimensional space with the help of some nonlinear function. Okay. So a famous example for linearly not separable input patterns is XR problem. We all know this. So in XR definition, what we have is, if the input pattern is 0 comma 0, then the output will be 0. If the input pattern is 0 comma 1, the output will be 1. If the input pattern is 1 comma 0, then the output will be 1. And if the input pattern is 1 comma 1, then the output will be 0. If you look into this outputs, there are two classes of outputs. 0 and 1. Okay, so therefore it is a binary classification problem. Now let us see whether these input patterns 0, 0, 0, 1, 1, 0, 1, 1 having these target values are linearly separable or not by drawing a hyperplane in the given input space. Okay, so now let us understand this. So the first point is 0 comma 0 with label 0, target label is 0. So where it comes over here. So 0 comma 0 is this with a label 0. Okay. And what is the second input label? 0 comma 1. So we took the measures here on x-axis and y-axis. It is 0 and 1. This is x-axis and this is y-axis. Okay, so 1 is labeled here, 0 is labeled here, 1 is labeled on y-axis here. So 0 point is the origin of the corresponding space. Now the second point is 0 comma 1 with input label 1, output label 1. Where it comes, x-axis 0, y-axis 1. So this is the point. Okay, so this is the point with label 1. Okay, now the third one, 1 comma 0 with label 1. 1 comma 0, where it comes, on x-axis 1 is here and y-axis 0 is here. So this is 1 0 with the output label 1. Okay, and then the fourth input pattern is 1 comma 1. Here it is, 1 comma 1 comes over here with the output label 0. Okay, so this is 0 0. Now if you see the output labels, 1 is here and 1 is here, 0 is here and 0 is here. Now if you try to draw a straight line that separates zeros with ones, try to draw, suppose if I draw a straight line over here, then it separates 0 onto one side, but another 0 is on other side. So what is required here is, we can say the surface is linearly separable if we can draw a straight line in such a way that the same type of labels comes on one side of the line and the other type of labels goes to the uh, other side of the line. So but here if you observe, if you try to draw a line anywhere, even if you draw anywhere, it will not separate the corresponding output labels into two exactly uh, different classes here. One of those zeros or ones will fall into other side combining with other output level. Okay, so you can see that it is clearly not separable in linear space. That means this input space is low dimensional. That is why we are not able to separate it linearly. Okay, so that is the problem here. Now, based on our previous covers theorem mentioning, what we can do is, if we can convert this input space into high dimensional space, then they can become uh, the linearly separable input patterns. Now let us convert this into a high dimensional space by considering some function, a special nonlinear function. Let us say we are considering a Gaussian function here, which is defined like this. Because there are two classifications required, I am defining two functions here. Phi1 of x is equals to e power minus norm of x minus t1 whole square, where this t1 is defined as 1 comma 1. Okay. So I'm defining two centers also to separate the patterns. T1 and T2 are the centers. So I'm defining phi1 of x to be e power minus x minus the first center T1. I assume the first center as 1 comma 1. It's not compulsory that you will go with 1 comma. You can go with any other label. Okay. Uh, but that belongs to the same input class. Okay. So here I took 1 comma 1, 0 comma 0, or else you can go with 0 comma 1 or 1 comma 0 also. So the second function, second Gaussian function I am defining is phi2 of x is equals to e power minus norm x minus t2 whole square, where this 2 t2 is a center that I took, that is labeled as 0 comma 0 with output label 0. So you need to understand that the output label of both the centers must be same whenever you consider centers. So output label of 1 comma 1 is 0 and output label of 0 comma 0 is also 0. Okay. right? So now, having defined these two Gaussian functions for the two classifications, phi1 of x and phi2 of x. Now, for each input pattern x, which is in XR definition, we need to calculate the new values of input space by applying this phi1 of x and phi2 of x on the corresponding input patterns. Okay. Now let us see how to calculate this. This table shows how to calculate that phi1 of x and phi2 of x for a given input pattern x. Okay, this is x. Now we apply phi1 of x here. The formula is, what is the formula for phi1 of x? It is equals to e power minus norm x minus t1 whole square. What does this mean? X minus t1 whole square calculates the Euclidean distance between x and t1. Euclidean distance between x and t1, that means 0 0 and the center 1 1, means square root of 0 minus 1 whole square plus 0 minus 1 whole square, that is going to be square root of 2, and it is because we have e power minus some value, so you will get this 0.1353 as phi1 of x. Okay, so you will get this value after applying e power minus of the value that you have. Similarly, phi2 of x can be calculated as, what is phi2 of x? Because the center is 0 0, this is going to be 0 0 minus 0 0, which will become 0. E power minus 0 is also going to be 1. Anything power 0 is going to be 1. So phi2 of x becomes 1 here for the input pattern 0 0. Now, if you observe, the input pattern 0 comma 0 is mapped into a high dimensional space as 0.1353 and 1. The values are changed, but the output label is still going to be 0. Okay, so now the new input pattern in the high dimensional space becomes 0.13531 with output label 0. So from here onwards, we will consider this as input pattern and this as output label. Okay. Similarly, we need to calculate the new labels for the remaining input patterns also. So for 0 comma 1, it will be calculated as 0.3678, 0.3678. So now this becomes the new input pattern in the high dimensional space with the label 1. Similarly, 1 comma 0 will be mapped to 0.3678 and 0.3678 with the output label 1. And finally, 1 comma 1 will be calculated as 1 0.1353 with output label 0. Now, every input pattern is mapped to some high dimensional input space, something like this. Okay, so we'll replace these values with the original input patterns in low dimensional space. So for our next checking for the linear separability, we will use these values, these points to represent in the hyperplane. Okay, and these output patterns for separating the input patterns. Okay, so let us see now whether these can be linearly separable when converted into a high dimensional space. Okay, let's have a check now. So what is our first point? The first point is 0.1353 comma 1 with output pattern 0. 0.1353 comma 1. 0.1353 comma 1 may be represented here with output label 0. Okay, so this is the first point. 0.1353 comma 1 with output label 0. Right. So what is the second point? It is 0.3678 comma 0.3678 with output label 1. So maybe it comes over here. Okay. 0.3678 comma 0.3678 with input output label 1. Similarly, third point is 0.3678 comma 0.3678 with output label 1. So this is going to be here. That means the same point with two output labels 1 and 1. Okay. And then the fourth one is 1 comma 0.1353. So probably it comes over here with output label 0. Okay. So now We have represented all the four input patterns in high dimensional space in this hyperplane. Now let us try to draw a straight line. See, you can draw a straight line now anywhere between these two positions. Okay, so you can draw anywhere here which separates the zeros and ones onto opposite sides. So you can clearly see that now the output labels zeros are on one side of the straight line, and ones are on the other side of the straight line. Okay. So what happened here? We failed to separate the input patterns when they are in low dimensional space, but we are able to separate them with a straight line when they are moved to that is when they are transformed to a high dimensional space. So that is what our Covers theorem mentions, and it is proved now with the help of an example also. Okay. Yes. So, in our previous examples, we tried to separate the input patterns linearly. So that is one possible way of separating the input patterns. But sometimes it is for a very complex problems of an input space, it is not always possible to separate them linearly with the help of a straight line. Then there are other possibilities of phi separable dichotomies also. Uh, Let us have a look at what are the other possible uh, separable dichotomies along with this linear separability. This we already know, assuming that this is one kind of input pattern uh, representing the labels X, and this is another kind of input patterns representing the labels O. And we can draw a straight line. Okay, then we call them as linearly separable. This we already saw. Now there is another one, spherically separable dichotomies. Okay, so what are spherically separable dichotomies? Let us imagine the situation where we have the output labels X like this, and output label O like this. Then you can use a shape to separate the labels like this. It's not possible to draw a straight line to separate the output labels here, but we can use a sphere to separate the output label O from the output labels X. So this is another way of separating your hyperplane. And the more complex problems can use this quadrically separable output spaces. Assume that these are the output labels X and these are the output labels O. It's not even possible to draw a straight line, or you cannot use a spherical shape to separate these also. Then in such case, what you can do is you can use uh, quadrics to separate the output patterns like this. Okay, so these two forms a quadrics. Two quadrics were used here to separate the output patterns O's from the output patterns X's. Okay, so it will be used when the input space is more complex. Okay. So these are the possible separable dichotomies we can use in our problems. Right. So that is about pattern separability and how the pattern separability and the covers theorem we discussed till now. Let us start the second topic of our concern today. That is interpolation problem. So what is exactly this interpolation problem is? So before we understand this, let us consider a neural network for imagination with one input layer, one hidden layer, and one output layer. Okay, we have in output layer we have a single neuron. Now assume this as input layer contains some neurons, hidden layer contains some neurons, and output layer contains only one neuron. So this is actually uh, a non-linear mapping from the input space to hidden space, followed by a linear mapping from hidden space to output space. If you imagine this as a mapping problem, then you can view that from input layer to hidden layer, it becomes a non-linear mapping. It will act as a non-linear mapping. And then from hidden layer to output layer, it acts as a linear mapping from hidden space to output space. Okay, so this is what actually it is performed in with the neural networks. Now let us put it in another way. Uh, Let us say we have a mapping S that maps R power P to R, where R power P is the input space and R is the output space. Okay, the interpolation problem statement is like this. If we have n different points, xi, let us say x1, x2, so on, xn, we have these points that belongs to the input space R power P. Okay, and also we have another set of real values. Di belongs to R, that means d1, d2, d3, and so on, dn, that represents the target values of these input points and different points. Okay, then the aim of interpolation problem is to find a function f such that when we apply that function on input pattern xi, it should result in the corresponding target value di. Okay, so the mapping is f of xi is equals to di for every I is equals to 1, 2, 3, and so on, n. That means f of x1 should map it to d1, f of x2 should map it to d2, and so on. F of xn should map it to dn. So it is simply the interpolation problem's aim is to simply identify a function that maps the input patterns from input space to some desired response di. Okay, so that is what the statement of interpolation problem is. Okay, so now we will go through what are the functions that are available to map these input spaces into output spaces. Generally, the radial basis function neural network employs a special function called as f of x is equal to summation of I is equals to 1 to n wi into phi of norm x minus xi. Okay, so this function phi of x minus xi is also called as a radial basis function, and each xi are the known data points from the input space. Okay, generally the xis uh, will be taken as centers of the network, that is based on the number of classifications that we need to make. So overall, the function f of x is equals to summation I is equals to 1 to n wi into phi of norm x minus x mi is used in RBF networks for calculating the mapping. Now, let us understand uh, how we can represent the relationship between this desired response and input patterns with the help of the weight matrix and a nonlinear mapping function. Okay, so let us assume that D and W represent some vectors representing the desired responses d1, d2, so on, dn, all to the power of t, representing it as a column vector, and weight vector w1, w2, so on, wn, all to the power of t, representing it as a column vector. So assume that these two are known, and weight vector we need to calculate that maps your input patterns into these desired responses. Okay, and let phi denote a matrix with elements phi is equal to phi ij, for ij is equals to 1, 2, 3, so on n, for every combination of 1, 2, 3, so on n, this will be calculated. Okay, so that means phi may be represented as phi 1, 1, phi 1, 2, so on phi 1 n. First row is calculated like that, and the second row is phi 2, 1, phi 2, 2, and so on phi 2 n, and so on like that. The last row becomes phi n1, comma phi n2, so on phi n. So this matrix is called as interpolation matrix. Okay, so now we have two column vectors d and w, and an interpolation matrix with size n by n, where there are n elements in each row and column. Okay. So now let us understand how we can represent the relationship between the interpolation condition and the function f. The linear equation that combines the interpolating condition as the function f can be represented in a matrix form like this. Phi into W, that is the matrix, interpolation matrix into the weight vector is equals to the desired response. This interpolation matrix is a representation of the low dimensional input space when it is converted to high dimensional input space. So phi represents the high dimensional input space into, we need to imagine some weight matrix that maps the corresponding input vectors into the desired responses. Okay, so the equation now becomes, the mapping equation now becomes phi into W is equals to D. Okay, then the unknown vectors, that is we need to calculate what, for what W this mapping will happen. Okay, so W can be calculated by using the formula W is equals to phi inverse into D. Because it is a matrix, we can easily calculate the inverse of the given square matrix into the desired responses T. Okay, so the weight vector which is to be known to identify the corresponding function that maps the input space into desired responses will be calculated as W is equals to phi inverse into D. Okay, so by using that formula, we can easily calculate the corresponding weight vector, and the weight vector represents even you can represent it in the form of a neural network also by mentioning the weights over there that maps your input spaces into output spaces. Okay, and now let us see what are the possible radial basis functions that can be used when solving the interpolation problem. We have already seen one example function over here, radial basis function, that is phi of norm x minus xi. This is a simple radial basis function we can use, and along with that we have few more radial basis function, variants of a few more radial basis functions available that can be used for mapping your low dimensional input space into high dimensional input space. The first one is inverse multi-quadratic RBF. Inverse multi-quadratic RBF is defined like this. Phi of R is equals to 1 by R square plus C square to the power of half R. You can write as square root of R square plus C square, where C is greater than 0 and R is greater than or equals to 0. The C is the center that we assume, and R is the value from input space, that is input pattern. Okay, so if you want to map the input pattern R into a higher dimensional space, you can use this formula 1 by square root of R square plus C square. This is a possible function which can be used for solving your interpolation problem. Okay, so what is the name of this? Inverse multi-quadratic RBF. Okay, and the other possible RBF that can be used for solving interpolation problem is Gaussian RBF, which is defined like this: phi of R is equals to e power minus R square by 2 sigma square, where sigma is greater than 0 and R is greater than 0, greater than or equals to 0. Here sigma acts as the standard deviation, and R is the center, R is the input pattern that we are considering. Okay, so the input pattern R can be mapped to a high dimensional space by using this formula also. Okay, so these are the two possible variants of radial basis functions which can be used in solving interpolation problems. Okay, so that's all for today. We have covered two fundamental concepts that are required in design of radial basis function neural networks. Uh, I simply give a glimpse of what we discussed today. We started with what is pattern separability. Pattern separability is trying to separate the given input patterns into two classes. We have seen some types of dichotomies also. If the input patterns are not linearly separable in low dimensional space, then the Covers theorem states that we can convert that input patterns from low dimensional space into high dimensional space. Then it will become easier for separating them uh, linearly. Okay, so that is what Covers theorem is stating, and we have seen that with the help of an example, the most famous example of XR problem. We have checked whether it is linearly separable in low dimensional space or not, and then we have seen after converting it into high dimensional space, we proved that it is linearly separable. So that is our first topic we discussed, Covers theorem and the pattern separability. And then we discussed about what is interpolation problem. We stated the interpolation problem as mapping the input patterns to desired responses with the help of a function. That means f of xi is equals to di for every input pattern, I is equals to 1 to n. Okay. So the aim of that interpolation problem is to find that function, and we have seen several possibilities of interpolation uh, functions that maps the input space into high dimensional space, starting with the radial basis function, general radial basis function, norm x minus xi. And then we have seen some variants of radial basis functions that can be used to solve interpolation problem also. Okay. And we represented the relationship between the interpolation matrix, the weight vector, and the desired response vector as phi into W is equals to D. Then to calculate the unknown vector with W, we use the formula phi inverse into D. Okay, so that's what we discussed today. With this fundamental knowledge, the basic knowledge, now we can discuss about what is meant by regularization and how it helps us in designing the radial basis function networks, uh, which will be discussed in our next class. So that's all for today. Thank you all for your patient listening. See you again in the next class.